Good morning, everyone. Today we'll be discussing multiplayer game search algorithms. We will uh, we will take you through the four major algorithms, and then we will try to summarize with some conclusions. So the two-player game search algorithms, the Minimax algorithms, are pretty popular, and if you look into literature, there are a number of robust algorithms that cater to even very complex two-player games. However, multiplayer game search algorithms are still a subject of active research, and this is owing to the complexities of player-to-player interactions. In real-life situations, like in auctions or in negotiations, where we see multiple parties bidding for the same object or same license, it's actually the multiplayer game algorithms which become more relevant. So today we'll be discussing the four major algorithms which we see in literature, and most of the other algorithms which appear in literature are actually variants of the four major algorithms. So I will start with the MaxN algorithm. This was first mentioned by Lockhart and Irani in the paper in 1986. So as you see on the graph on the right side, uh, we have similar to the Minimax algorithm. Each player makes a move alternatively. So player one, player two, and the player three makes a move, and the payoffs are denoted by a set of uh, n numbers, which denotes the payoff of each player at that node. For example, at this point, A1, B1, C1 denote the payoff of the player one, player two, and player three. The end node uh, the end node values can be either an exact payoff or it can also be heuristic evaluations. And at each node, the player tries to choose the player who is moving at that point tries to choose the maximum of the set. For example, in this case, player three will try to choose the maximum of C1 and C2, and which will and then make a move accordingly. So just to give you an example, this is a simple example where again there are three players. So if we start to the bottom node, player two will have to choose between these two uh, payoff sets. And since four is of course greater than three, so player two takes this move. In this case, actually, interestingly, the payoff player two uh, payoffs in these two nodes are the same. So it's three both. So typically there's a tie-breaker algorithm wherein the players have which the players have to follow. And in this case, the player two takes the payoff from this side, which results into the 2-3-5 move. And if we go one more node up, player one, of course, has to maximize his payoff. So he chooses the left side node. So the root payoff is 541. As in the other the two-player min-max algorithms, pruning algorithms are very important in order to not only analyze complex games but also to make sure that computational time and resources are at the minimum. Unfortunately, uh, pruning algorithms from MaxN are not very robust. I've been mentioning two of them now. The first one is called the shallow pruning, which was discussed in the paper by Koff in 1991. Sorry, this is given a minimum and a maximum bound for the player's goals, and the minimum bound is 0, and the maximum bound for the sum of all the scores is 10. So if you look into the graph here, at node A, player when player A goes to left side move, he knows that he can get 5. So his payoff should always be greater than 5. Now, if you come to node C, uh, when player when player 2 moves, His move is he goes into the left side and then he finds that his payoff can be 6, which means that the sum of the payoffs for the other two cannot be greater than 4, which means player A cannot be greater than taking greater than 4 at this node, which implies that player A will always be choosing this node, and that's why all other childs of this nodes can be pruned. Another one of the famous pruning algorithm for maxn is called the speculative pruning, which works in quite a similar way. For example, node A, again, if he goes to the left side node, he knows that he will always get greater than 5. When player 2 makes his move and he goes to the left hand side, he finds 3, and that's why his ultimate payoff has to be greater than 3. This leaves only 5 plus 3, 8. So, like I mentioned, the max bound was 10. So, this leaves only 2 as a payoff for the third player. And when we come to the third level, we see this node actually has 2 for player 3, which means there cannot be any better payoff for the player 3. And that's why these nodes can be pruned. Now, the main drawback of this pruning algorithm is we haven't even yet explored the branches of the top node. So it might result in a different payoff structure for the top node if we were to expand these nodes, which is typically not a problem, because as long as we expand the other nodes of B, we can always get back to the same payoff structure. But that, of course, also means that we have to expand more and more nodes, and which kind of defeats the purpose of pruning. Now, coming to the main shortcoming of the maxn algorithm, which I mentioned earlier on, in case a player finds a tie between his payoffs, there's typically a tie breaking rule. And in this example, player 2 chooses the left side node. Had it chosen the right side node, it would have resulted in 6-3-1, which means player 1 would have chosen this side as well, and the ultimate payoff of the game would have been different. And that's actually the main shortcoming of this algorithm, that tiebreaker rules can sometimes arbitrarily affect the value of the tree. Now I'll let my colleague run you through the rest of the algorithms for multiplayer games.
Hello everyone, my name is Aradhya Sawant and I will be explaining you how the paranoid algorithm works. So in practice, almost no pruning occurs when we use Maxent to play multiplayer games like Chinese checkers. The lack of pruning in Maxent has motivated research into other methods which might be able to search faster and deeper into a multiplayer gameplay. The paranoid algorithm reduces the multiplayer game to a two-player game by making the paranoid assumption. The algorithm assumes that all opponents have formed a coalition against that root player. While the paranoid player tries to maximize his or her score, all coalition players try to minimize paranoid player's value instead of maximizing their own. By doing so, regular alpha-beta pruning is possible, which leads to a larger search depth. Let us have a look at the game tree or min-max tree of a hypothetical game where three players play a single round. Player 1 is the root player, and player 2 and 3 are the coalition players. As discussed, root player will try to maximize the value, and coalition players will try to minimize the value. Player 1 has two possible actions, player 2 has two possible actions, and player 3 has only one possible action. Let us briefly discuss how paranoid algorithm operates under the hood. The paranoid algorithm starts by exploring the nodes in DFS order of traversal. Search starts from node A, then node B, followed by its child nodes D and E, having values -2 and -3. Since B is a minimum node, its value will be the minimum of child nodes D and E's. Hence, node B is given the value -3 and A is also passed the value of -3. In the next step, the algorithm explores C, followed by the first child node F, having the value -4. As the value of C will be less than or equal to -4 because it is a minimum node, the algorithm does not need to explore the other child node of C. Similar pruning can be achieved by using alpha-beta algorithm and is based on the same logic. If all the players play optimally, player 1 will play move 1 and player 2 will play move 2, and the score of the player 1 will be -3. If player 1 plays move 2, which is not optimal, player 2 will play move 1 and the score will reach -4. Let us now discuss the advantages of using paranoid algorithm. First, since alpha-beta pruning is possible, the algorithm can reach larger depths in same computational cost. Second, paranoid algorithm may outperform other algorithms due to the larger look-ahead. Let's discuss the shortcomings of paranoid algorithm. First, paranoid algorithm gives us a single paranoid value, which is the guaranteed lower bound on one's score. This may, however, be lower than the actual score achievable in the game. For example, in Game of Hearts, paranoid player may conclude that there is no way to trick other players with the Queen of Spades. But instead of forcing the opponents to work as hard as possible to make this happen, the algorithm may select a line of play that causes this to happen immediately. As number of players increase, the coalition dominates the root player, which leads to more suboptimal play and less efficiency. Now, I will hand over this presentation to my friend who will explain how the best reply search algorithm works.
Hello all, I am Bharti Chaudhary and I'll explain the best reply search algorithm. In best reply search algorithm, we assume that not every opponent is trying to minimize the root player score. Only one opponent is actually minimizing the root player score. Only that opponent which has the strongest counter move value against the root player that will be selected. To get that one, at the min player node, all possible moves are generated for all opponents. Let us see the best reply search algorithm step by step. Now alpha beta values are the lower bound and upper bound values of the game tree at that particular depth. Turn variable alternates between the max player and min player. If depth is greater than 0, the following steps are evaluated. For max player, all possible moves are generated, and for min player, all possible moves for all the opponents are generated. And for all the moves, the value v is returned with the negated sign and with the negated sign of beta and alpha values. If the return value v is greater than or equal to beta value, then this value will be returned, and alpha is the maximum value between the previous alpha value and the value v, and finally we'll return the alpha value. Now let us see one example. The example is of a three player game tree. So root player node is the player 1 and player 2 and player 3 are the opponent players with min node. From the terminal node values we can see that we have the minimum value of 2 for the player 3, and this node will be selected. This node value is selected for the main player node, since this needs the minimum value with beta as 2. Now this value is returned to the player 1. So player 1 has the alpha value initially with minus infinity, and this value so 2 is compared with that. So since 2 is greater than minus infinity, we will consider the alpha value as plus 2 here. And now let us see the other possible move of player 1. So here we have the value 1 for player 2, and this value 1 is actually less than the alpha value, and we can't get any value greater than 2 here, which can maximize the player 1 node. So since alpha value is greater than or equal to beta value, the regular alpha beta pruning happens here, and the other node values are terminated. So some advantages of best replace search algorithm. We will see some more max nodes which are visited along the search path, and this leads to long-term planning of the game tree. And it relaxes some assumptions over Maxon and Paranoid, where Maxon assumes that no players are forming the coalition against the root player, and Paranoid assumes that all the players are forming the coalition. Best replay search algorithm is able to prune the parts of the tree. This leads to reduced computational complexity. The disadvantages of best replay search algorithm goes as follows. Not all the players are allowed to make a move, and the opponent moves which are beneficial for the root player might not be considered. So, not an appropriate method for trick based card games such as hearts and spades. Thank you. So, the following part will be taken up by Shubhra Shankar Chatterjee. Thank you.
Hello everyone, I am Shubhashankar Chatterjee and I'll be discussing about the multi-minimax algorithm. The minimax principle has been shown to be an effective scheme for playing the two-player games. Compared to traditional two-player game playing, multiplayer environments, through the addition of other self-interested agents, introduce a range of new complications and challenges. These include any single player's gain need not lead to an equal loss among the opponents. Players' coalition can arise even in games with only a single winner. The board state can change more between the prospective players' moves. A single valued heuristic is not always sufficient to appraise the game state. The established pruning schemes, for example, the alpha-beta pruning, are not always applicable. The computation is exponential with respect to the number of players. Despite these challenges, due to the historical success of Minimax with alpha-beta pruning in a wide variety of domains, substantial effort has been dedicated to extending it to the multiplayer environments with various levels of success. One such example is discussed out here, which is called the multi-minimax algorithm. The goal of this algorithm is to find a way to significantly increase the search depth for the prospective player in a search tree algorithm for playing multiplayer games in which the players are allowed to move simultaneously. One drawback of previously mentioned solutions is that their asymptomatic runtime is exponential with respect to the number of players and the depth of the search tree. If an effective solution is found for one game, it could then be possibly applied to others non-turn based simultaneously played multiplayer games. The method we proposed in this particular algorithm, it can be seen as the BRS with a very aggressive pruning method, which makes it so that minimizing players cannot alternate taking turns against the maximizing player. Given the current game state, the maximizing players plays n-1 different games against each of the n-1 opponents and makes a move, assuming that depending on the next move the maximizing player makes, the maximizing player will be playing the rest of the game only against the best opposing player for that move. To describe the multi-minimax algorithm, we invoke the minimax algorithm, which is used as a subroutine for multi-minimax. Observe that when n is the number of players, b is the branching factor, and d is the maximum number of game rounds. This is a visual representation of the multi-minimax algorithm with 3 players and a branching factor of 2 for each players. Each node represents a game state and is labeled with players whose turn is next down the search tree. Each edge represents a player's move. Nodes with multiplayers have their outgoing edges labeled to indicate which player moved. So the first node is 1, that is the first player will move. It has 2 branches, meaning that it has 2 options. If it chooses the first option, then again the node has 2 and 3 as its label, meaning that it can be a move for either player 2 or player 3. For player 2, again it branches to uh, two different nodes, and it again then it returns to 1, and again it goes to 2, and for it happens for 3 as well. So this is a basic example of a multi minimax algorithm. Now there are some salient features that needs to be discussed. For a given heuristic used for a game, the newly proposed scheme, the multi minimax, and the added pruning method were more effective than the alternate solutions. Here, the alternate solution means the previous algorithm discussed, that is the paranoid search and the BFS and MaxN. The details of this experiment can be found in the paper that's given in the link that's mentioned below. That is multi minimax, a new AI paradigm for simultaneously played multiplayer games. Again, both methods provide largely increased search depth along with a minimal loss in exploring important board states, thus being more effective. Here both basically means multi-minimax and DFS search. There are a few disadvantages as well. Multi-minimax could prove its ineffectiveness in games where players can much more easily work together to eliminate the other players due to it being too similar to Minimax. Again, multi-minimax could be ineffective in games where searching realistic board states is much more important than having improved search depth. In summary, I would like to discuss that multiplayer games have always been a challenge uh, in the history of AI. They involve the perspective player to search through combinations of a certain move order which may or may not truly represent the move order of the game, and to try and predict which next move in the game would be most effective. The new algorithms try to address some of the issues of the max-n and paranoid algorithms as well. Most of the latest research are devised on these 4 key algorithms, and out of these 4 algorithms, multi-minimax has proved to be the algorithm with it has proved to be the state of the art algorithm. That's all for this. Thank you.